Hi, this is Mark Weissman. Welcome back to this fifth video on partial differential equations. I want to work with problem 8.3 in Mathews and Walker Mathematical Methods of Physics. This is a little bit more involved, and we'll have to use some properties of Bessel functions in this video, but the basic idea is no different than for Fourier series. So let's start. I'll read the problem. A sphere of radius r is at temperature T equals 0 throughout. At time T equals 0, it is immersed in a liquid bath at temperature T0, T0. Find the subsequent temperature distribution, capital T, of radius and time inside the sphere. And we'll call kappa the thermal conductivity per density per specific heat. I'm not going to go into the physics on what that means, but we know from our previous equations that we have that the diffusion equation that governs this temperature distribution. I have a little bit of a notation conflict here because usually capital T would represent the time function, but in this problem capital T is always going to be temperature. So I'm going to just write the time functions directly. So the Laplacian of the temperature minus 1 over kappa times the partial derivative of the temperature with respect to time equals 0. This is our standard diffusion equation. And the boundary conditions are that the temperature at radius r time is equal to T0, and this happens for all, say for all T greater than 0, and the temperature at any radius but at time T equals 0. That's any radius less than the radius of the sphere. So basically you can think of it as if we just have a sphere, radius r, and it's being immersed in water, and the water has a temperature T equal T0, which is not going to change. So on the boundary we're always going to have T equal T0. We start out with 0 in here at time T equals 0. Eventually this is going to come to temperature T equal T0 after a long period of time. So we use the standard separation of variables technique. I'm going to call the separation constant k squared equal to lambda over kappa. This defines lambda as well. And what we're going to find is that the temperature as a function of r and t, I'm leaving out the angular variables now. That'll actually be in the equation, but you'll see in a moment why I'm leaving them out. YLM is not equal. This should be proportional to YLM cosine theta, spherical harmonic, square root of lambda over kappa times r times e to the minus lambda t. And now it's easy to see physically that everything here is spherically symmetric. we start out the boundary conditions. We have an inhomogeneous boundary condition at the radius r, capital R. We have t is capital T naught. So we have an inhomogeneous boundary condition. We have a boundary condition that holds for all r at a given time, and it's 0. So everything we have is spherically symmetric. So it should be intuitively obvious using the boundary conditions. It is intuitively obvious that the solution is spherically symmetric. And only the only YLM components are L equals 0, which requires M equals 0 also. If you want, you can prove this using the orthogonality properties of the spherical harmonics. I'll just write them down. Those who have a physics background have seen this thing many times. I'm using my older notation. Works very well. It's just like the Fourier series and everything, and the spherical harmonics are extremely useful because they're an orthogonal set of polynomials, but they are complex, so we have to use the star here. I'm not going to go through this proof. Like I said, it's intuitively obvious that the solution is spherically symmetric. So we can write down the solution. T is equal to T0 plus the sum over n, some constant an, times, when L equals 0, M equals 0, Y0, 0 is just equal to 1 over the square root of 4 pi. So it's just a constant which we fold into the an. J0 KNR e to the minus kappa kn squared t. And I define kn by knr is the nth root of the spherical Bessel function. So J0 KNR equals 0. And so let's just see what I've written down here and why it's a solution. First of all, this is the particular solution that takes care of the inhomogeneous boundary condition. So you can see if we put R equal R, we get Kn capital R. J0 Kn capital R is 0. So this whole term is 0, and we just get T equal T0. And that's what we want. Now, the other boundary condition we have to satisfy is the one at time t equals 0. So at time t equals 0, substituting t equals 0 in here, we're going to get minus T0 is equal to the sum over n, an times J0 KNR. So this will satisfy this boundary condition, because when we put t equals 0, we get this here, then we add the T0 and we get 0. So this is the equation that we have to solve, And this is sort of analogous to a Fourier sine series. And we have to determine the coefficients an. So, in analogy with a Fourier sine series, this I think is sometimes called a Fourier Bessel series. And we can use the same techniques to evaluate the an. First thing we need some properties of spherical Bessel functions. And the best way to get these is to look them up in a book or online. So if you look in Chapter 7 of Mathews and Walker, and you do some manipulation. Chapter 7 is on special functions. If you ever want to know about Legendre polynomials, spherical harmonics, Bessel functions, and various other functions, that's a good place to start, as any other mathematical physics book is also a good place to start. I'm going to use an equation that comes from that book, and it's sort of analogous to the with the Fourier series, only this time it's a little bit different. Anyway, the integral from 0 to r of the spherical Bessel function knr times another spherical Bessel function kmr. See, here we're using the two different roots. R squared dr takes care of the measure for the spherical case. This is equal to del mn. I'm sure you're all familiar with the Kronecker delta. That's equal to 1 when m equal n, 0 when m unequal to n. So we have delta mn r cubed over 2. Now we have a spherical Bessel function of the first order. Notice the difference between the 1 and the zeros. J1 k n r squared. So, using this, we'll now use this equation in here. What we'll do is we're going to multiply this by J0 kmr and integrate from 0 to r. So what we get is minus the integral from 0 to r t0 J0 k m r. I have to multiply by a different index, so I'll use m because I already have n on that side. R squared dr is equal to the sum over n, the integral from 0 to r, an J0 knr, that's just all these terms. We multiplied by J0 kmr r squared dr. Now here we're going to, on the right side here, we're going to use this formula which is tailor-made for it. So this is equal to sum over n an del mn r cubed over 2 J1 kmr squared. And this is equal to, because the only term that contributes here is when n equal n, this is equal to am r cubed over 2 J1 kmr squared. Okay. Now, so this implies, running out of room here. This implies that AM dividing this by this, AM is equal to minus the integral from 0 to r, T0, J0, KMR, r squared dr divided by r cubed over 2, J1, Km, capital R. Okay, so now we'll use some properties of the Bessel functions, which I alluded to in the previous couple of videos. First of all, J0x is equal to sine x over x. So the mth root is m pi. So this implies that Kmr is equal to m pi. I'm going to use this a lot. Also, J1x is equal to sine x minus cosine x over x. If I substitute KMR here, I get J1 KMR is equal to J1 m pi, and this is equal to sine of m pi is 0 and the cosine of m pi is negative 1 to the m. We have another minus sign, so this is equal to negative 1 to the m plus 1 divided by m pi. X is m pi. So that sort of helps us evaluate the denominator now. Now let's carry out these integrals. So AM is equal to minus 2 T0. The 2 comes there, the T0 there. R cubed. Now J1 KMR, it's going to give us an m pi. Oh, I forgot. So J1 KMR squared, we don't have to worry about the negative 1 anymore, so it's just equal to 1 over m pi squared. So now I have, it's 1 over m pi squared in the denominator, so that becomes m pi squared. Now I have the integral from 0 to r. Now using the formula for the spherical Bessel, of order 0, I get sine KMR divided by KMR multiplied by r squared dr. Okay. This is an easy integral to evaluate because it's when you change variables, if you use x equal m pi capital R times r, use that substitution, then this is just going to be equal to, I'm not going to show it here, but you can easily verify it, minus 2t0 over m pi, the integral from 0 to m pi of x sine x dx. This is just equal to minus 2t0 over m pi minus x cosine x plus sine x evaluated at 0 in m pi. We can quickly check this antiderivative. The cosine x gives me a minus sine x, so that gives me the x sine x. And then I'm left with a minus cosine x, which is canceled by that cosine x. The sine evaluates at m pi and 0 doesn't do anything. and this one doesn't do anything at 0, so it's just minus m pi times negative 1 to the m. So this whole thing ends up equaling 2 t0 negative 1 to the m. I'm sure I'm going to lose a sign here. Okay, that's right, yeah. Because I have, this one gives me a negative 1 to the m, then I have two negative signs there. Okay, so now we can write down our whole solution. T of r comma t, this is temperature, radius, and time, is equal to t0 plus 2t0, the sum from m equal 1 to infinity, negative 1 to the m, this is the an part, sine, remember we have j0 in our expansion, j0 knr, which is just, I'm using m here, but sine m pi r over capital R divided by m pi r over r, that's the spherical Bessel function, times e to the minus kappa m pi over r squared t. So this whole thing is our answer. And usually what you find is the dominant term is the m equal 1 term. The bigger m is, the faster it will decay exponentially to 0. So if you want to know the dominant term at a reasonable time, you just take the m equal 1 term. But what I'd like to show is, or at least discuss, is let's show that this is in fact a solution. It's not obvious to us. Don't usually verify partial differential equations, but let's just show it. So the first boundary condition we have to verify, t of r comma 0. We substitute it in there. This term goes away, and we're just left with t0 plus 2t0, the sum from m equal 1 to infinity, negative 1 to the m, sine m pi r over r divided by m pi r over r. Now, we need this to be equal to 0. For that to be equal to 0, we need this whole thing in brackets here, right after the 2, to be equal to minus 1/2. It's not obvious that this is minus 1/2, but if you take the Fourier sine series of a sawtooth wave, you can prove it. And I'm not going to do that for you here, but you should be able to show this from using the Fourier sine series. And the other thing you want to verify is that this solves the differential equation. And this is just this is actually very easy, because you need to just show that when you take the del squared t, because the angular variables are gone, it's just equal to 1 over r, the second partial with respect to r2 of rt. And so you can just differentiate the series and calculate that. And then you also want to verify that that's equal to 1 over kappa partial of t with respect to t. And that's also easy. You just differentiate this term. And if you do this carefully, you'll find out that, in fact, this thing does solve the partial differential equation. And if you use the Fourier sine series of a sawtooth function, you'll find out that, in fact, this holds, and this is equal to -1/2, and we solved all the boundary conditions. So thank you very much, and I'll continue on problem 8.4 in the next video. Thank you.